If you're stuck on any of that stuff, I can help you. But right now, we do need to do, there's one thing I want to do with you guys today. I'm going to introduce the next concept. So find me this page. And then when it says concept, it should say concept number 2. And I'll be honest, I'm not sure why they put it here. To me, it doesn't make an abundance of sense as to why this particular concept goes where it does. So at the top of this, don't scratch it out like some people have done in the past, but on the top of this page, what I'd like you to do is I'd like you to write the word skip. And we're going to come back to it in, I want to say about 4 weeks. The very last lesson we do, we'll come back to this page. So then I want you to, after you've written skip on that page, I want you to flip 1 page, 2 pages, and find me this, where it says names and formulas of compounds. And this is where things start to get a little fuzzy, because I think you did some of this stuff in grade 9. Depends on who you had. Did any of you have Mr. Morrison for Science 9? Okay, I know Morrison's kids always do this. If hands up if you had Easton for Science 9. No. O for Science 9. Did O's crew name things? Did you do any chemical formula naming with O? Okay. Or did you both have O? Okay, so O's crew. I'm just asking you guys specifically. Anyone who had O last year, you did this. Okay. Krishka, who'd you have? Gill. Hands up if you had Miss Gill. Did Miss Gill's class do any of this naming stuff? A bunch of you are saying no. Hands up if you had Carr. Did Carr's class name formulas? Okay. Broad. Hands up if you had Broad. No, she didn't have any science last year. Okay. And that's everybody, I think. Did anyone have someone different at this school? Miss who? Rosa? Kosa. Kosa? Who's Kosa? Oh, she was the sub for Miss Gill. So you had Miss Gill. Okay. And we've already established that Gill didn't do this. Okay. So this will be reviewed for some, it won't be for others, and that's okay. I don't think it's technically part of the Science 9 curriculum, but here we go. So, naming and formula writing. These things all there are conventions that were laid down for how these things get named. In 1919, which feels like a really long time ago, it's 106 years ago now, a group called the International Union of Pure and Applied Chemistry. That is quite the name. We abbreviate it now. It gets abbreviated to IUPAC. And for the longest time, I never knew what this meant. When I was a university student, chemistry was not my major. My major was physics. My minor was math. I did chemistry in high school, but this was never referenced. And we got into chemistry in high school, and they started talking about, oh, yes, the IUPACs, the IUPACs, the IUPACs. And I'm like, what the frig is an IUPAC? Anytime something is labeled as being IUPAC, comes back to this 1919 convention that got together. They called themselves the International Union of Pure and Applied Chemistry, and what they did was they established convention and standards for the language of chemistry. What this means is that it does not matter where in the world you go. The rules for chemistry are exactly the same. Whether you're doing chemistry in China, Japan, Korea, Turkey, the Czech Republic, Brazil, wherever, it all happens the exact same way. And so they established convention and standards for the language of chemistry, specifically relating to how things are named and expressed as chemical formulas. Form U plus. And if they didn't establish these things, especially because the early 1900s was really when the world, as the entirety of the world, started to cooperate with this stuff. World War I was done. Air travel had roughly just been invented. Between air travel and rail and various other communication tools had been established. Now, chemists in all of these different countries could start to actually get together. And when they got to get together, they have to be able to communicate, even in their own languages, but what they're creating, what they're naming, and so that's where this was established. And so what we're going to do here is we're going to look at a bunch of these different naming rules. We'll likely only get the first couple done today, and that's fine, but I want to show you what these are. So, ionic compounds. All of the naming that we're going to do today and tomorrow is going to relate to ionic compounds specifically. Covalents have their own name. An ionic compound, for review, is a compound that is formed between what two kinds of elements? I heard someone say it. An ionic compound is formed between metals and nonmetals. The positive ions and the negative ions attract each other because opposite charges attract each other, and the chemical compounds then form. So it says that, which is basically what I'm saying here. The compound is formed between attraction between positive ions. Leave some, don't fill up that whole space with that word because I got something else I want to add there. And negative ions. Negative ions. Don't fill up that whole line there either because I want to go back and fill something in there too. Dominic, you gave us names for these. You threw down some language that I had not used yet. What did you call positive and negative ions last week? Positive ions are also called cations. Can we read that color? Yeah, that's a good color. Cations. And I'd never heard this before, but my student teacher 2 years ago was a science student teacher. And he said that an easy way to remember, and it was brilliant, an easy way to remember that positive ions are also called cations is because cats have paws. And he wrote it like this. He said positive, which is kind of adorable and definitely spelt incorrectly. That is not how you spell the word positive. But it's an easy way to remember, oh yes, you're going to have cations, and Dominic, you said that the negative ones were called anions. So an easy way to remember which is which, the positive ions and the negative ions, is that the positive ions are called cations because cats have paws. And so there's all of the naming rules that we're going to look at now and tomorrow are ionic compound naming rules. The first looks like this: naming ionic compounds. There are a whole bunch of ionic compounds that are really quite simple. We're going to start with the simple ones. The simple ones are called binary ionic compounds. Binary ionics. Does anyone know what that word binary means? That's fine. Binary means two. Bi means two. So a binary ionic compound is just two simple ions, one positive, one negative. And how these things get named is that the metal is said first. Whatever the ionic compound is, the metal always gets to go first. The nonmetal, the negative ion, the cation or the anion, the nonmetal is given the suffix IDE. Now, if you recall what a suffix is from way back in elementary school, it's an ending. You change the ending of the name, and it gets an IDE thrown there at the back. And it does not matter how many of each atom there is in an ionic compound because they will figure themselves out. As you saw when I had on the assignment that you guys are working on right now, I said just make me the thing that involves magnesium and chlorine, and you guys some of you stumbled through it. You're like, oh, I got a magnesium, I got my chlorine. You assumed it was going to be 1 and 1, and then you looked at it and said, well, chlorine only has room for 1. And magnesium wants to give up 2, so what's the deal here? Some of you figured it out on your own, some of you asked me, some of you talked about it amongst your peers, and you said, well, the only way this is going to happen is if a second chlorine shows up to take that other magnesium, because I didn't specify how many of each you needed to figure that out. And out in the world, in the environment, when these things bond with each other, it's never one atom and one atom. It's always clumps of things or groups of these things that come together. And they figure out amongst themselves how they need to arrange themselves so that everybody's happy. And when we look at, put a star here, when we look at covalent compounds, that's not true. Because covalent compounds are the ones that share, and they sometimes share in different ways. So the metal is said first, the non-metal is given the suffix IDE, and I've got a bunch of examples for you here. So you guys can get used to where that IDE gets placed. This one here, fluorine. Fluorine becomes fluoride. And all of the ones that end in INE, those are easy to fix. The INEs become IDEs. Fluorine becomes fluoride. If you look at the periodic table, chlorine becomes chloride, bromine, bromide, iodine, iodide, oxygen. And this is where things get weird. Because it's oxygen, and the oxide takes over at the at the Y. The YGEN gets dropped, and that's the portion that disappears to become ide. So it's not oxygenide, as I've seen students read and write before. It's oxide. Sulfur becomes sulfide. This one is selenium. Because the I is already there, it's pronounced selenide. Nitrogen becomes nitride. It takes over at the O, the last two syllables. And then phosphorus becomes phosphide. So this is phosphorus. And you kind of just got to get used to where those things get placed. It seems like for those of you who are really into the English language and enjoy like counting syllables of things, and you're into the grammar of and the construction of the English language, because I know those people exist, it seems like it always happens at the second syllable. So fluorine, 2 syllables, fluoride, 2 syllables. Oxygen is 3 syllables. At the second syllable, the ij portion is where it takes over. Oxygen, 3 syllables, becomes oxide, 2 syllables. For those of you who are looking for a rule that seems to be like a decent one. So then when we name these things, it's all relatively straightforward. Magnesium and phosphorus, the metal name doesn't change. Magnesium is the metal, so it just gets named magnesium. The non-metal, phosphorus, comes next and becomes phosphide. That's it. Now, it doesn't stay this simple because it would be lame if things stayed the same. And I had some students have complained in the past, or not complained, but expressed their frustration. Here, sulfide is spelt with an F. If you look at your periodic tables, if I'm not mistaken, sulfur there is spelt with no, that one spells it with an F. Some places you'll see it spelt like a PH. That's just the difference between British spelling and American spelling. The Brits will spell it with a PH, the Americans will spell it with an F. But it means the exact same thing, whether it's sulfur with an F or sulfur with a PH. So then what's the name of calcium and chlorine? Calcium chloride, that's it. The metal comes first. Calcium, chlorine becomes chloride. So the next one would be sodium iodide. Aluminum and oxygen would become aluminum oxide. And strontium and bromine would become strontium bromide. And at this stage, that's all we need. Now we're going to change it up here in a second because things get more interesting here. Take a look at a periodic table that you can see clearly, either the big one at the front or the inside front cover. What do magnesium, calcium, sodium, aluminum, and strontium all have in common? What do magnesium... yes, they're all metals, but give me more than that. What do magnesium, calcium, strontium, aluminum, and... magnesium, calcium, sodium, aluminum, and strontium all have in common? They all what, sorry? Oh, You're getting warmish, but no. Look just at the periodic table. What do they are? There is something that these 5 metals and other ones have in common, but these 5 have in common that is different than some other metals that show up on that periodic table. Nope. They are not all on the same shelves. Nope. How many possible ion charges do all 5 of those things have? What kinds of ions do those things form? No, what? Sorry, how many different kinds of cations do they form? Magnesium, if you look at the charge on magnesium, what is the possible charge for magnesium? +2. Calcium? +2. Sodium? +1. Aluminum? +3. Strontium? +2. And if you look at the periodic table, there are other metals hiding out there. There's a whole bunch of metals. If I grab my pointing stick, roll it at it, Sean. There's a bunch of other metals. So all the ones that I've chosen there are metals where if you look up in the top right, or top, and this one's top left, on yours it's top right. If you look up in the corner, you're going to see all of these examples that I've given you only have one kind of ion. In a second, actually probably tomorrow, there is a different set of naming rules for any metal element that has multiple ion charges because it matters what charge is being used. So at this stage, the naming rule that I've given you, and I want you to make on the note here on the bottom of the page, this is for metals with one charge. Because there are other metals that don't just have one charge and they behave differently. Okay, when you're ready, flip the page. We're going to go the other way. Once we've got the name, now we need to actually build the formula. How do these things come together? Without drawing Lewis and Bohr diagrams every single time we need to know. The formulas will tell us. So, it should say ionic here. I don't know why the IO disappears every time. When you're writing the formulas for these things, there's a set of rules for that too. Ionic charge isn't, because these are ionic compounds, ionic charge is important for indicating how many of each ion are involved in the compound. Like I said, they will figure this out on their own, but you need to be able to do that too. When 2 atoms react ionically, they react so that the compound they form, remember ionically is a positive and a negative. When they get together, the compound they form is neutral. Means it has no charge. Were we asking what neutral meant, or were we asking what he was writing? And I'll flip back and show you an example of what I mean. Like if we flip back here, I'm going to flip back. You don't have to flip back. Where is my answer key to that? Here we go. So when we drew a Bohr diagram, no, those are Lewis diagrams. We drew a Lewis diagram for MgO. MgO now has a name. What's the name for MgO? Mg is magnesium. Magnesium oxide. We drew, this is the Lewis diagram for magnesium oxide. When these guys come together, you've got a positive 2 and a negative 2. 2 positive 2 plus negative 2 is 0. There's no charge. Lithium and fluorine. This is lithium fluoride. Lithium's got a positive charge. Fluorine's got a negative charge. When they come together and interact, +1, -1 is 0. Okay? Interesting. What about some of these other ones? A bigger one. I've got beryllium fluoride, BeF2. Beryllium has a charge of +2, and look, there's 1 fluorine there, there's 1 fluorine there. The total charge on an ionic compound is always 0, because that's how they want to arrange themselves. And they also do this, they also react so that they have the least amount of each element necessary. They could go in larger amounts, but they don't. They always go in lowest. It's like lowest common denominators when you're dealing with, or lowest terms when you're dealing with fractions. They always want to arrange themselves that way. So what compound forms between magnesium and chlorine? I'll do this example for you. And this will probably, and then there's a couple practice ones. It's not so bad, and then this is where we'll call it a day. So first of all, now we've got a name for magnesium and chlorine. What's magnesium and chlorine called when they come together? Magnesium chloride. And that pen is also dead, so let's move on to this one. Magnesium chloride. And here are the steps for figuring out how these things are going to come together. The metal is always going to get labeled first, because it always does. You want to write down the elements separately with their charges to the top right. So magnesium is Mg. When it ionizes, it's going to have a charge of +2. And chlorine is going to have a charge of -1. Now, the longer way to do this, is to ask yourself, okay, if I'm bringing groups of +2 and groups of -1, what is the smallest amount of each atom necessary to create a neutral compound? Or another way to think about it, what's the smallest number that goes into 1 and 2? 2. No, I'm thinking about it back. The smallest multiple of the common multiple of 1 and 2 is what I want. Is 2. So to do that, how many magnesiums am I going to need? To get me +2 charge, I only need 1 magnesium. I don't know what's funny. To get me -2 chlorine, how many chlorines am I going to need? 2. So 1 +2 and 2 -1s is how we create magnesium chloride. And then when we actually go ahead and write the formula, we're almost done. We're not quite done. Anytime you see a 1, you don't write it. So then this thing would just be MgCl2. And the reason for this is because magnesium's +2, chlorine's -1. 2 times 1 is 2. 2 times -1 is -2. And so you get these charges balancing out. So the formula would be MgCl2. And if you go out into the world, we know this to be true. Fortunately, there's a shortcut for this. And here's what it looks like. The shortcut for this looks like this. Where you want to write down the elements separately. Again, metal first. With their charges to the top right. So, I'll do the exact same example. We've got Mg with a charge of +2 and Cl with a charge of -1. With going kind of through it the more cumbersome way, look at what happened here. The charge on magnesium was 2. The charge on chlorine was -1. And oh, look. The charge ended up being the amount of atoms of the amount of ions of the other kind. So magnesium had a charge of 2. Chlorine was 1. So I needed 1 magnesium and 2 chlorines. Effectively, what we did, one way to think about what we did was, well, we swapped these numbers and dropped them down to the bottom. The 1 that was up on the chlorine went down on the magnesium. The 2 that was up on the magnesium went down to the chlorine. And it's a quirk of finding the lowest common multiple of something. The easiest way to find the lowest common multiple of something is to multiply those two things together. And so then this is part of the shortcut. What we're going to do is we're going to swap and drop the charges. So to figure out what the formula is going to look like, I'm just going to take these two numbers, bam, bam. And then anywhere where there's a 1, we don't have to write it. This is just going to become MgCl2. Let's do another example of the same kind of thing because there's another step here, something to be aware of if you're going to take advantage of the shortcut. The other example I want to do with you is this guy here. Let's look at calcium oxide. If you were going to make calcium oxide, let's go through the steps. We've got Ca, we've got O. The charge on calcium is what? +2. What's the charge on oxygen? -2. So if you guys were drawing Bohr diagrams, and I think you even did in your assignment, you did this. How many of each of calcium and oxygen would I need to balance out their charges? I would need one of each. So then I should just be able to write that this thing is going to become CaO. If you're going to use my shortcut, what you'd write down, you'd say, okay, I've got my charges there. I'm not even going to think about it. I'm going to swap. I'm going to drop. And you're going to get Ca2O2. But we know it's not supposed to be that. As part 1 said, it's going to be CaO because I only need one of each. So what do I have to do? What's my third step here if you're going to start to adopt the shortcut? We're not, almost. We're not going to cancel. There's a different math word we're going to use. Starts with an R. Ooh, no, that's an awful math word that I don't want to bring into science class. I mean, it's a great math word in math class, but reciprocal would be a terrible math word to bring into science class. We want to reduce. Swap, drop, and reduce if necessary. So when I say reduce if necessary, what can I divide anything out of 2 and 2? Yeah, I can divide them both by 2. Divide by 2, divide by 2. That gives me one of each. Oh, look. I now have one of each. I don't have to write the ones, and I get what par 1 said we were supposed to get in the beginning. So if you're going to use the shortcut, you got to make sure that you're thinking it through this way. You got to make sure we swap, drop, and then reduce if necessary. And sometimes they get interesting, especially when you're dealing with the stuff in the middle of the table. So what I'd like you to do in the next, there's about 3 minutes left in the block, I want you to give me the formulas for these 8. Crank them out. Write down the symbols, write down the, yes, you need a periodic table. Write down the symbols, write down their charges, and then either do the long way or swap and drop your way to figuring out those 8. You should be able to get all 8 of those done in the next 3 minutes if you haven't done so already. Don't pack up yet. I want you to do those 8. Don't pack up yet. Crank them out. Get them done. Okay, get them done. Start writing down charges. Symbols and charges. Give her. All right. Get your stuff up. Ready, get set. Get your stuff up. Act when I tell you to. Or when the dog. So what? You can get all 8 of those done to this. That's not a big reason why not have. What? I didn't write it's the first day. To the I don't
When you coach this one be like them.
Trying to see how this is. What box is that? Yeah, that's right. Okay, have a good day. What?
No,
Feel right?
I don't understand.
Go get the box tomorrow. Yeah, but why are you? What is the circuit for?
Would be man. Well, you got ready.
Show me the order here. How would you do something like? I'm not put a taxi in
Put it in your bag, man.
I kind of want to and everybody goes to bed or owes clocks, man. Yes, you guys are.
And then you connect them. Then there's one more. Okay, and again, to make it easy. Still one for the disconnect until the.
Yes, if you would like to do that much work, you are welcome to do that much work. Where I would say, okay, I've got, my math brain says, well, I've got +2 and -3. What's the smallest number that 2 and 3 go into? No, that they go up into.
Oh.
Common multiple of 2 and 3. Goes 2, 4, 6, 8. 3 goes 3, 6, 9. So that's it, 6 and 6. So I need 3 of those and 2 of those. That's 2 times 3 is 6, 3 times 2 is 6. You can draw a bunch of boxes if you want, or just look at this and say, oh look. Yeah, ZN3 P2. You're done. So I like to approach it from like, I think it's way less work to approach it mathematically, but if you want to draw a bunch of pictures, I never would stop you. You're just gonna take way longer to do it. Which I'm hey, if that is what you want to do, that's a cool method. I'll show it tomorrow. Yeah. Make sure I do it properly, but I will absolutely show that what you just done, I will show tomorrow as an option for sure. It's cool. It's a lot of work, but it's cool. Okay, see you guys later.
Okay.